Good afternoon, everybody. Welcome to the SciPOP lecture series. The Hong Kong Science Museum has the pleasure to present this lecture. Today, we are honored to have Professor Junming Zhong, Professor, Department of Physics, the Chinese University of Hong Kong. And Dr. Leung Hoi Dick, Lecturer, Department of Physics, the Chinese University of Hong Kong. The topics of these lectures are studying the fundamental structures of matter and the universe at the Large Hadron Collider and seeing with particles and non-electromagnetic waves. At the end of the lecture, we would have about 10 minutes for the question and answer sections. The lecture is about to begin. Professor Zhu, please.
Thank you. So welcome to the talk. I'm MC Chu. So as you can see, my initials are MCC or MC squared. Okay? So please call me MC squared rather than Professor Chu. So today, I and Dr. Leung together would like to introduce to you some of the methods that scientists, especially physicists, have been using to study structures of matter and space-time. I should go back to the very beginning, sorry. We just finished a long talk in Cantonese. Okay, I believe that a main driver of science throughout the years has been the curiosity of people about all kinds of things in our world, in the universe. How come we have all sorts of structures and seemingly very different kinds of matter in our universe? So it all starts from some curious kid, 1 meter in size, and we slowly explore the world around us, both in the microscopic side, until we found the atoms around nanometer size scales. Or we go the other way around and we discover that the so-called solar system and Earth is just an ordinary planet around the sun. And this is already much bigger scale than our daily life length scale. We keep going, and then in the recent years, we now understand that atoms are made of elementary particles which are believed to have sizes even smaller than 10 to the minus 18 meters. So this is an imagined drawing of what's inside the proton. At the other extreme, we build bigger and bigger telescopes, and we now know that solar system or our sun is just a typical star. We are part of the so-called Milky Way galaxy with about 100 billion suns. And even the Milky Way itself is just a very typical galaxy. There are billions and billions of galaxies in the universe. So this is one of the largest structures that we know in the universe, the so-called Virgo supercluster. So each dot here is already a galaxy, typically about 100 billion suns. So all the way from 10 to the minus 18 meter to 10 to the 21 meter, we already have tools to study. And we believe that we pretty much know something about all the length scales between the very small and the very large. We believe that we understand some of the rules, how it works. How come we have atoms? How come the quarks get together to form the protons? Or how the matter comes together to form stars, form galaxies, form galaxy clusters, and so on. So today, the theme of our talk is to introduce to you some of the methods, how scientists have been doing this, how we have been studying all these structures, as well as some of the more important results. So the idea is if I give you an object, and if you like to understand the structure of it, so what's inside, right? It could be really quite a mess inside it. People kept looking. One important breakthrough was, of course, the discovery of atoms. So this is a real picture of atoms. And we've been able to image atoms, individual atoms, for many years now. But we didn't stop there. Because we kept look inside atoms, now we know the structure of atoms, and we even know the structure of the atomic nucleus, which is a tiny, tiny size, about 10 to the minus 12 centimeter in length scale. We know that an atomic nucleus is made of protons and neutrons, but we can even probe deeper than that. We now know that protons and neutrons are made of quarks and gluons inside there. And outside the atomic nucleus, we know that there are electrons. So today we have the view that the truly elementary particles are the electrons and the quarks. They made up the atoms which made up everything that we know of. But we don't even stop there. Of course, we want to know whether there are other more elementary particles inside electrons and quarks. So we keep searching for the ultimate atoms, as well as the rules that govern how they behave, how come they get together to form all these various structures. So that is the main driver of development of science. After many years and many people's efforts and a lot of money, we now have a standard model of particle physics. We believe that these are the truly elementary particles. So we have 6 types of quarks, 3 types of electrons. The usual electrons we know is the lightest one, but then there's also a muon and a tauon, which have almost identical properties as electrons, except for the masses. And then we also know that there are 3 types of so-called neutrinos, which I'll come back to slightly later. All these are believed to be elementary particles, which means that everything is made up of them. And they interact by exchanging another kind of particles called gauge bosons. Photons, gluons, W and Z. Exchanging photons would give rise to electromagnetic force. Exchanging gluons gives rise to strong force. Exchanging W and Z gives rise to weak force. Then, of course, we also know that there's gravity. They also interact through gravity, perhaps by exchanging gravitons. I did not put gravitons in this picture because we don't quite know how to understand gravity yet. 4 years ago, a very important breakthrough was the discovery of yet another boson called the Higgs boson, which is different from all these photons, gluons, W and Z. I'll come back to the Higgs boson near the end of this talk. So we now understand that ordinary atoms are made of protons and neutrons and electrons, and the protons and neutrons are made up of quarks. So these composites of quarks and gluons are called hadrons. For example, a proton, a lot of people will say it's made up of 3 quarks, but then actually that's wrong. This is closer to a true picture. If you really can look inside a proton, you find that there are many, many different quarks and anti-quarks, as well as infinite numbers of gluons. They're exchanging the gluons, interacting, and the strong force will then bind this soup of quarks and gluons together to form the protons and neutrons we know of. Okay, so how do we probe the structures of matter? There are three ideas that we'll cover in this talk. The first one is the simplest. So give me a garbage can. I want to know what's inside it. The easiest way is to just measure what it emits, okay? Just the smell, whatever. Okay? Measure what comes out, and then you can guess what's inside. Second way, if you're not satisfied, you can shoot some particles in. And some of these particles will then be scattered by the content of the object you want to study. So that's scattering. And by recording the scattering pattern, you might be able to reconstruct what's inside there. Third way, the most violent way, let's just break it up. Okay? So let's do collisions. We bang two garbage cans together, destroy the cans, and see what's inside. Okay? That's pretty much what we're doing at the Large Hadron Collider. So we bang together protons at high energy to look inside them. We will cover examples using all three ideas. And the topics we'll cover include the following. So first, I'll give you some very brief introduction. The first topic is how we make use of neutrinos to study astrophysical objects, such as exploding stars and so on. Second topic, I'll be very brief. I'd like to introduce you to the idea that the so-called gravitational waves that are emitted by astrophysical objects, and if we can detect them, I strongly believe that we haven't been able to do that yet, but I strongly believe that we're very, very close to be able to doing that. Then there's a completely new tool to study the universe. And then Alvin, Dr. Leung, will take over to discuss how we can make use of particles like electrons and neutrons to see the structures of matter. So this is about electron microscopy and crystallography, which enable us to study structures of proteins, for example. And then I'll come back to talk about the experiments at the Large Hadron Collider, how we make use of very high energy particle collisions to study properties of elementary particles. So we'll go from macroscopic world, astrophysics, cosmological scales, down to more sort of daily life length scale, and then down to the truly microscopic world. That's the plan of the talk. So let me start with neutrino astrophysics. Neutrinos are believed to be elementary, so they are not made up of other particles, right? We know that there are three types: electron type, mu type, tau type. They do not have electric charge, so there's no electromagnetic interaction. They interact only through the weak force and gravitational force. We don't know yet what the masses are, but we now know that the mass is tiny, must be really, really small, but non-zero. Now, out of all the elementary particles I told you about, the quarks, the electrons, and neutrinos, if you count the number of them in the universe, then actually neutrino is the most abundant in the universe. There are many, many more neutrinos than electrons or quarks. But a very special property of neutrino is that they don't interact much at all. They're very inert. Give you an example. The sun is producing many electrons every second. I'll tell you the number. But take a typical solar neutrino. If you want to stop it, it will take rocks, 10 light years of rocks, stack them all together, then with this amount of matter, on average, you could have one neutrino interaction on average. So it's that difficult to stop them. That's why they're called ghost particles. Okay, so our sun, this is a true picture of our sun. I put our Earth here, not at the right distance scale, of course, but just want you to feel the sizes. Okay? So we receive a lot of sunlight and energy from the sun, and it's believed that sunlight is produced by so-called fusion reactions at the core of the sun. The sun would turn 4 protons into a helium nucleus, but every such interaction would produce 2 electron-type neutrinos. So every second, there are 2 times 10 to the 38 electron-type neutrinos produced in the core of the sun, and they penetrate through the sun, almost no interaction, and spread out to the universe. Some of them will get here. On Earth, every second, every centimeter squared, we get about 400 billion of such neutrinos. They just pass through the Earth, and you receive a tiny fraction of them. So every second, your body would get about 10 to 16 of such neutrinos passing through you. Okay? And none of them do anything to you, don't worry. Okay? But if you think about it, the sun is just a very typical star. All the stars in the universe, throughout their life, would keep on burning, turning protons into heliums, turning matter into energy by Einstein's famous equations, E equals mc squared. And a fraction of that energy actually come out in the form of neutrinos, about half of them. Okay? So you can think of neutrinos as the ghosts of matter. So the thermonuclear reactions turn matter, ordinary matter, protons, and so on, into light and neutrinos. And these neutrinos don't die. They will exist forever. Just a side remark, the 2015 Nobel Prize in Physics was awarded to these 2 physicists, Kajita and McDonald. They built huge neutrino detectors, one in Japan and one in Canada. And these you can now think of as neutrino telescopes because they are measuring neutrinos from the sun. Other than stars, another major source of neutrinos are supernovae. Okay? So supernova is an exploding star. We believe that all stars with mass a few times that of the sun, when they die, they will have to explode. Explosion is a very violent event, so that the star would become very bright for a brief duration of time. So this is just an animation of that. So this star blows up. This is not the supernova explosion yet. Now comes the supernova explosion. Right? Now, but the main point of this animation is that if you can only see with ordinary light, with visible light or even X-ray, whatever, you cannot see anything. Because this fireball is not transparent to light. You can only see the light from the surface. You cannot see inside. You don't know what's going on in this explosion. But we also know that this explosion, all these explosions, produce a huge amount of neutrinos. Typical supernova should produce 10 to the 58 neutrinos in seconds. And these neutrinos can penetrate through the fireball, and they'll come to Earth. So if you build a neutrino telescope, you can easily see through this fireball to really study what's going on inside this supernova explosion. So a supernova is a violent event, but actually more than 90% of its energy is carried away by neutrinos. So if you can see with neutrinos, you can really study these explosions very well. These have been observed. Supernova neutrinos have been observed. Okay? So 1987, there was a star that blew up. This was before the explosion, after it. It's called supernova 1987A. Okay? So here I show you a plot by several neutrino detectors in the world, especially these two, Super Kamiokande, which is a Japanese experiment, IMB is the United States. Okay? So within a short period of time, within about 10 seconds, both detectors suddenly receive a large burst of neutrinos with a lot of energy. And by the timing difference and the location and so on, they can actually triangulate to the location they know that comes from here. Okay? So these are the supernova neutrinos that we have already seen them. Okay? So this demonstrates that, in principle, we can really study objects like supernova by building neutrino telescopes. Now, we have a supernova 1987. We're still waiting for the next one that's visible to us. Okay? But at least we are ready. We, I mean Hong Kong scientists. Okay? We have been involved in an experiment in Taipei, 50 kilometers from here. We have built neutrino detectors, 8 of them altogether. Each one is about 5 meters high, 5 meters in diameter. They're hiding in the mountain very close to the Taipei nuclear power plant. So the original motivation of this experiment was to study the neutrinos from the reactors. Okay? But we have modified it so that if there's a supernova and if it emits a lot of neutrinos, if it comes to Hong Kong, well, they must, right? Then our detectors would know. Okay? We'll see sudden bursts of neutrinos and we will know that there's a supernova somewhere. So actually, I will be the first in Hong Kong to know if a star blows up. So I talked about the neutrinos from the sun, from the core of the sun. I talked about neutrinos from a dying star that blew up. Right? But the really most powerful explosion is, of course, the Big Bang. So we now know that the age of the universe is about 13.8 billion years. Today, the universe is very cold, but there are lots of evidences that we now know the universe began as a very hot and dense fireball, the so-called Big Bang. And because it's so hot and dense, it must also produce a lot of neutrinos. So these we call cosmological neutrinos. If you can detect these cosmological neutrinos, that means you can really study the Big Bang itself. Much better than visible light, because again, visible light cannot get out of this Big Bang. We haven't been able to do that yet. But this is a long-term dream of physicists, that one day, if we can measure these cosmological neutrinos, then that will be fantastic. And there are lots of them. They're everywhere, even inside this room, inside your body. Everywhere in the universe, every centimeter cube, there should be about 300 of these cosmological neutrinos. They're all around us. Okay? So the question is whether and how eventually we're going to measure these signals from the Big Bang. So that's neutrino astrophysics. Let me switch to the second topic. Another tool. Yet another tool which, again, is very penetrative. It's so-called gravitational wave. Okay? So what are they? Now, 2015 is actually the 100th year celebration of Einstein's theory of general relativity. Let me summarize what that theory tells us. Okay? The basic idea of the theory is summarized in this one sentence. Space-time tells matter how to move. Matter tells space-time how to curve. So imagine that the space-time is like a deformable medium. Okay? Now, space-time is empty, so how do you think about it, right? So try to imagine the following. In space, every meter you can make a point, make a mark, and then imagine there's a time axis. Every second you make a mark. Okay? You join all these marks, you form something like a net. Okay? General relativity tells us that if you put matter or energy, they're equivalent, then they will curve the space and time around that matter. So let me show you an animation. So this is my space-time. If I put a sun in here, it will curve the space and time around it so that another planet, like an Earth, come around to this region, will feel the curved space-time and naturally follows an orbit. So this is how Einstein's general relativity explains gravity. Of course, it's not really just such a simple theory. If you really want to learn it, there's a lot of mathematics involved. But the key idea is that Einstein treats space and time as a deformable medium. If it's a deformable medium, think of a string. That means you can pluck on the string, and then the string will vibrate. Okay? So similarly, if I grab the sun, shake it up a little bit, then the space-time around it would not only curve, but there would also be waves produced in space-time. Such waves are called gravitational waves. In the theory, they propagate at the speed of light. And you will feel the gravitational waves because the stretching and squeezing of space and time can show up as displacement of objects on it. So imagine that I put a ring of masses. If there's no gravitational wave, then I still have a ring. But if a gravitational wave passes through, then it would distort the positions of these masses in this way. So this is how we're going to measure or detect gravitational waves. Now, in the universe, we believe that there are many objects that will produce a lot of gravitational waves. Okay? One very prominent candidate is black holes. Okay? So I think everybody knows black holes is a lot of mass collapsed into a very small size. Even light cannot get out. But now if you have a binary system, two black holes, and if they orbit around each other, then the disturbance to the space-time around that system would emit a lot of gravitational waves. It would be very violent motions and violent disturbance of the space-time. Another possibility is another kind of very compact stars called neutron stars. So these are solar mass stars shrink down to about 10 kilometers in size. We already know that there are binary neutron star systems. So two neutron stars orbiting each other will produce a lot of gravitational waves. Let me show you an animation of two neutron stars orbiting each other. And these patterns you see are the gravitational waves they will produce. So hopefully, if we have a gravitational wave observatory, we can measure these waves, and then we can really study these exotic systems. And then, of course, violent explosions such as the supernova or the Big Bang itself would produce a lot of gravitational waves. Okay? The only problem is that usually these are very far away. So the gravitational waves, when they propagate to Earth, will be very, very weak. And so up to now, we still have not been able to detect gravitational waves yet. But people are working very, very hard. I believe that we are very close to be able to do that. Let me turn these waves into sound so that you can hear the sound of two neutron stars orbiting each other. Okay? Now, of course, these are not real sound because sound cannot propagate in empty space, right? But we just make an analog of these gravitational waves because I just like you to get a feeling of how this wave would change in frequency. Okay? That's beautiful music, huh? So you can notice that the frequency goes up, right? Why? Because these objects, when they orbit each other, by the emission of gravitational wave, the orbits will then shrink. Eventually, they will merge together, so we call them mergers. When they merge together, there might be some explosions, or if these are black holes, then a bigger black hole will form. Okay? So these are very interesting objects to study. So I told you already that it was 100th year last year of the birth of general relativity. 1 year after that theory, already Einstein knew that there should be gravitational waves. So this year is the 100th year anniversary of that. I hope we will celebrate that by detecting gravitational waves. And once we can do that, astrophysics will not be the same because we have a completely new tool, very much powerful tool to study exotic objects like black holes, neutron stars, Big Bang, supernova, and so on. I did not talk too much about gravitational wave astrophysics, but I like to advertise that one of my new colleagues, Professor Johnny Lee of CHK, is a member of LIGO, which is the most advanced gravitational wave detectors in the world. He's a member of LIGO. One of our undergraduates actually worked there last summer. And in February 12 and 19, Professor Lee will give a more detailed talk about gravitational wave astrophysics. On the 12th, the talk will be in Cantonese. On 19th, it will be in English. Okay? So if you're interested, please come to CHK for this talk. I assure you that it will be very interesting and very exciting. Okay, now, let's turn from the macroscopic, from astrophysics, from cosmology. Now let's get back to this Earth, to our Earth, okay? And Dr. Leung will then take over to talk about microscopy using particles.
Thank you, Professor Chu. Hello, everyone. I'm Alvin Leung, a lecturer at the Chinese University of Hong Kong. Today, I'm going to talk about how to use non-electromagnetic waves or particle waves to see atoms. Now, this talk is a journey into the atomic world. And we are going to start from this real world, going down to the molecular world, and eventually going to the atomic world. The magnification from the atomic world to this real world is about 1 billion times. You may ask, how large is 1 billion exactly? Outside, we've got Victoria Harbour, and the width of Victoria Harbour is about 1 billion times the diameter of a strand of hair. So you can see that the atomic world is really, really small. And what's so amazing about this talk is that both the theory and the experiments were only possible in the last century. Now, as you know, our wave has got 4 properties. And on the screen, you can see 4 pictures Each picture represents a particular property of wave. On the top left, you can see a very beautiful scenery with mountains and lake. The lake acts as a mirror. You can see the reflection of the mountains and the sky. So this is an example of reflection. And on the right-hand side, you can see a glass of water together with a spoon. The spoon looks a little bit bent. This is because the waves travel at different speed in different medium. This is an example of refraction. And at the bottom left, you can see water ripples overlapping, and the amplitudes of the waves add up. This is an example of interference. And on the bottom right, you can see water wave expands upon reaching the open space. And this is an example of diffraction. We'll return to the last two properties later on. Now, when I talk about seeing matter, most likely you are going to associate it with optical microscopes. In optical microscope, we put our sample on the platform and we look at the sample through the optical microscopes. Optical microscope uses visible light, and to characterize wave, we need to know the wavelength. The wavelength is defined to be the distance between two consecutive peaks in your wave. In visible light, red light has the longest wavelength, about 700 nanometers. Violet light has the shortest wavelength, about 400 nanometers. So how long is 700 nanometers? Well, that's about the size of a bacterium. So you can see that the wavelength of visible light is really, really tiny. We are going to look at some small objects, but some objects are smaller than the others, and we are going to look at them one by one. A strand of hair is in the range of millimeter, and then red blood cell is about 1,000 times smaller in the micrometer range. Bacteria is about another 10 times smaller. Viruses is about nanometers in size. Antibodies, the molecules that fight against pathogen in our bodies, are about 10 nanometers in size. DNAs and nanotubes, they are about nanometers in size. And then finally, we arrive at atoms, which are on the scale of angstrom. We can use optical microscope to see cells and tissues, but can we use optical microscopes to see atoms directly? As you probably know, atoms are made of nucleus and the surrounding electrons. The nucleus is made of positively charged protons and uncharged neutrons. The size of the nucleus is about 10,000 times smaller than the size of an atom. As Professor Chu has mentioned, protons and neutrons are made of quarks. Quarks are about another 10,000 times smaller than the size of the nucleus. In order to use wave to see matter, the wave has to interact with either the electron or the nucleus. Now back to our original question, can we use optical microscope to see atoms directly? The answer is unfortunately not. We cannot use optical microscope to see atoms directly. This is because the image becomes blurred due to the diffraction of light. Now suppose I've got an aluminum foil and I make a hole in the middle and I shine the light through. I put lenses in the middle to refocus the light. If there's no diffraction of light, then I would expect to see a very sharp image. However, due to the diffraction of light, then I see a collection of concentric rings. To understand why this is the case, on the screen I put two figures. You can see the yellow arrows indicating the light waves. I make a hole on the cardboard. We call it an aperture. When the aperture is large, there's not much bending of light, and when I look at the image is sharp. However, when I slowly decrease the size of the aperture, bending of light occurs. It turns out that diffraction and interference play a very important role. Due to the time limit, I'm afraid I can't go into the details, but the end result is the image consists of a collection of bright and dark rings. The most important message is that when there's a small aperture, the image becomes blurred. This has a very important consequence. When I put 2 point sources together, separated by a distance d, the distance d is very similar to my wavelength. Now, on the top row, you can see where I put the 2 point sources. When I look through the microscope, then I see 2 blurred images. Now, when I slowly decrease the distance between the 2 point sources, the 2 point objects start to join together. When I further decrease the distance between the 2 point sources, the 2 objects merge together. When I can tell the 2 objects apart, we say that we can resolve the 2 objects. However, when I can't tell the 2 objects apart, we say that we cannot resolve the 2 objects. We say that the microscope has reached the resolution limit. It turns out that the resolution of a microscope depends on the wavelength of the wave I used. In an optical microscope, the resolution limit is about 200 nanometers. And as I have mentioned, the size of an atom is about 0.1 nanometers. So the resolution limit of optical microscope is about 2,000 times the size of an atom, and that's the reason why we can't see atoms using an optical microscope. So what can we do? Luckily, in 1924, there was a breakthrough. De Broglie proposed that all matter has wave-like property. The de Broglie wavelength lambda is equal to the Planck constant, h, that's the value of the Planck constant, divided by the momentum p. By increasing the momentum p, we can decrease the wavelength. We can use different types of particles, including electrons, protons, and neutrons as wave. By changing the momentum, then we can change the wavelength. If the wavelength is in the Angstrom level, that means there's a possibility that we can see atoms directly. Now, as an example, let's calculate the wavelength of an electron with an energy of 1 kilo-electron volt. As we all know, the kinetic energy is equal to p squared divided by 2p, where p is the momentum and m is the rest mass of the electron. We know the rest mass of an electron is 0.511 mega-electron volt divided by the speed of light squared. When we plug in all the values, then you can find out the momentum. That's 31970 electron volt divided by c. Now we use the de Broglie relation and then put all the values in, then we get the wavelength to be 0.039 nanometers. That's smaller than the size of an atom. If we use this electron beam as a wave, then there's a chance that we can see atoms directly. In 1931, Max Nord, a German engineer, and Ernst Ruska, a German physicist, successfully built the first electron microscope. And in the picture, you can see Max Nord on the left-hand side and Ernst Ruska on the right-hand side building their electron microscope. At that time, the magnification of the electron microscope was only 400 times, which was much worse than the optical microscope at that time. However, soon afterwards, Ernst Ruska built a second electron microscope that has a better optical resolution than an optical microscope. In the late 1930s, the resolution of an electron microscope has reached 10 nanometers. And at present, the resolution of an electron microscope is 0.05 nanometers. In 1986, Ernst Ruska received a Nobel Prize in Physics for his fundamental contribution to the development of electron microscopes. On the screen, you can see two types of electron microscopes. On the left, you can see a transmission electron microscope. And on the right, you can see a scanning electron microscopes. In both types of electron microscope, the electrons are produced by the electron gun. Electrons accelerate from the negative terminal to the positive terminal. If the power source is stable enough, all electrons have the same energy when they pass through the positive terminal. All lenses in electron microscope, they are magnetic lenses. Between the electron gun and the sample, you can find the condenser lens. The condenser lens controls the intensity of the electron beam. And also, it makes sure that the electron beam is narrow. We put the sample on a stage here, which is movable, and the sample is in vacuum. Now, in transmission electron microscope, the electron beam penetrates through the sample. We use an objective lens to refocus the electron beams. And we use a projector lens to magnify the image of the electron beams. There are two advantages in using multiple lenses. Firstly, we have a more flexibility in magnification. Secondly, we do not need to increase the size of the microscope. The electron hits the fluorescent screen at the bottom of the electron microscope, and then we process the image digitally. Normally, electron microscope images are in black and white, but we can also color the image according to other experimental data of the sample. We can also color the image of artificially. Now, on the right-hand side, we've got the scanning electron microscope. The working principle of the scanning electron microscope is very similar to the transmission electron microscope. In scanning electron microscope, the electron beam has to be focused to a fine point, and then we use these electron beams to scan through the whole surface, point by point. And then the detector measures the number of electrons that are either bounced back from the surface or ejected from the surface. Then we put all the data together to generate an image. On the screen, you can see a comparison between transmission electron microscope, TEM, and scanning electron microscope, SEM. In TEM, we detect electrons that are transmitted, and in SEM, we detect electrons that are either bounced back or ejected from the sample. In TEM, the accelerating voltage is higher because we want the electron beams to penetrate through the sample. The resolution is also higher in transmission electron microscope. In TEM, since the electron beam has to penetrate through the sample has to be thinner. In SEM, the electron beam has to be focused to a fine point, but there's no such requirement in TEM. So far, we have been talking about the principle of electron microscope. Now, let's take a look at some practical applications. At present, we use electron microscope in material science and medical science. And in medical science, we use electron microscopes to see viruses and bacteria. On the top left, you can see a TEM image of influenza virus. And on the bottom left, you can see an SEM image of HIV virus together with white blood cell. The HIV virus is in green, and the lymphocyte is in pink. On the top right, you can see the aerospace alloy. You can see the 5 nanometers mark. At this resolution, you can see each individual atoms directly. Maybe it's a bit blurred on the screen, but if you look at the PowerPoint on the computer, then you can see it clearly. At present, SuperSTEM, which stands for Super Scanning Transmission Electron Microscope, produces image of the highest resolution. And in the bottom right, you can see an image of some iron compound. At this resolution, again, you can see each individual atom directly. So my point is that electron microscopes are very powerful in comparison to optical microscopes. Okay, at this point, I would like to make a diversion. I just want to ask, does anyone in the audience know what this picture is? You can just shout. So to give you a hint, this related to a very important biological question in the 20th century. Oh, I can hear something in the back. Exactly. So this is the X-ray diffraction pattern of DNA molecules. It has a name. It's called Photograph 51, and it was taken by a scientist called Raymond Gosling. Watson and Crick use this picture to deduce that DNA has a double helix structure. Since this technique led to such an important discovery, I think I'm going to spend some time on explaining what X-ray crystallography or X-ray diffraction is in the coming 10 or 15 minutes. In crystallography, we want to find out the arrangement of atoms in a crystal, and nowadays we use it in material science or medical science. To do crystallography, we need two things. First, a crystal, and then a wave source. There are many examples, everyday life examples of crystal. One example is table salt. The chemical formula of table salt is sodium chloride. If you zoom into a grain of salt, then you can see a regular pattern as shown on the screen. So the green ball represents the chloride ion. The blue ball represents the sodium ion. This regular pattern is very essential for diffraction. Now, the first step in crystallography is to grow a crystal. Growing a crystal is very difficult. The crystal has to be small, and also it has to be pure. This is the requirement of the crystal. What about the wave source? As we've mentioned, when the wavelength of the wave is similar to the size of an opening, then that's diffraction. The distance between neighbor atoms in a crystal is about angstrom. That means if the wavelength of the wave is similar to angstrom, we can obtain diffraction. If you look at the electromagnetic spectrum, that corresponds to X-ray. Of course, we're not only limited to X-ray, we can use any type of waves as long as it has a wavelength in the range of angstrom. If we use electron waves, then we can obtain electron diffraction. If you use neutron waves, then you can obtain neutron diffraction. Of course, the interaction of X-ray, electron wave, or neutron wave with matter, they are all very different, but the underlying principle of the diffraction is very similar in each case. In the last century, we have solved many important scientific problems using X-ray crystallography already. And on the screen, you can see two molecules. On the left, you can see a molecule called hexamethylbenzene. You can recognize the benzene ring in the middle. Now, if you ask any high school students who are studying chemistry nowadays, they can instantly tell you what a benzene ring is. A benzene ring is planar, and also the 6 bonds in the benzene ring, they are of equal length. However, a century ago, the story was completely different. Nobody knew the structure of hexamethylbenzene. In 1929, Kathleen Lunster determined the structure of hexamethylbenzene using X-ray crystallography, and her results suggested that the benzene ring in the molecule contains delocalized electron. On the right-hand side, you can see red blood cells. Red blood cells are responsible for the transport of oxygen within a body, and the main component of red blood cell is a protein molecule called hemoglobin. In 1937, Max Perus began his PhD study, and at that time, he wanted to use X-ray crystallography to find out the structure and the function of hemoglobin. But at that time, nobody has used crystallography to solve such big molecules before, and many scientists were very skeptical about whether that's going to work or not. But Max Perus was very persistent in his work. He spent the next 15 years trying to solve the structure, and in the end, he made it. Nowadays, these two molecules are standard textbook examples, but a century ago, they were complete mysteries. It shows that science progresses very quickly. Okay, back to our talk. Now, we want to measure the diffraction pattern. How do we do it? So we use a machine called Bragg spectrometer, and on the right, you can see a diffraction pattern. We put the crystal at the position shown here. The X-ray tube produces X-ray. The match filters ensure that the X-ray of a single wavelength can pass through. The collimator ensures that the X-ray beam is narrow, and the X-ray hits the crystal, and the detector measures the diffraction pattern. We can rotate both the crystal and the detector. Now you can see the diffraction pattern contains a lot of dots. So what is that dot? What are these things? In fact, these dots contain information about the arrangement of atoms in a crystal. You can see it as an encrypted message. Once you decode the message, then you can find the arrangement of the atoms in a crystal. To understand why the diffraction pattern looks like this, I've included a diffraction gradient pattern on the screen. And on the screen, you can see a light bulb together with two slits. The light wave travels from the light bulb through the two slits. And due to diffraction, you can see intermittent bright and dark fringes on the screen. Now, my question is, what happens when the distance between the two slits decreases? And on the right, you can see an animation showing what happens when the distance between the two slits decreases. Now, when the two slits, this distance between the two slits decreases, the bright and the dark fringes separation increases. You can see it. Now, when the distance of the two slits increases, the distance between the bright and the dark fringes decreases. Imagine these two slits represent two atoms. When the two atoms are close by, that means the distance between the bright and the dark fringes is large. Conversely, when the two atoms are far apart, then the distance between the bright and the dark fringes decreases. That means we can work out the distance between the atoms from the diffraction pattern. Now, so far we've been talking about slits in one direction, in the vertical direction. If I add another slit in the horizontal direction, what happens? You can see the diffraction pattern on the right-hand side. It looks quite familiar. It's similar to the X-ray diffraction pattern we have seen before. At this point, I would like to do a short demonstration on three types of diffraction grating. In the first one, the slit separation is large. In the second one, the slit separation is small. And in the third one, we've got slits in both the horizontal and the vertical direction. And we're going to use a red laser beam to shine through the slit. We're going to make a comparison between the distance between the bright spots. Now, let's go for the first one. Okay, Professor Chu is doing the demonstration. You can see that, this is the central bright spot, and the two other ones quite weak on the side. Now remember the distance between the bright spots. Now we switch to the second one, and you can see the distance between the bright spots should increase. We can go back to the first one and then quickly go to the second one to do the comparison. Okay. So the important message is, so when you compare the distance between the bright spots, then you can work out the distance between the slits. Now, if we shine through the third diffraction grating, then you should be able to see a very nice diffraction pattern. The third one. It's quite vague, but you should be able to see two dots above and below. Okay, anyway, that should be similar to the X-ray diffraction pattern we have seen before. Oh, thank you, Professor Chu, for the demonstration. Okay, let's get back to the talk. Now, on the screen, you can see a crystal lattice, and you can see two light beams. Light waves traveling by path A is reflected by atoms in the first layer, and light waves traveling by path B is reflected by atoms in the second layer. Path A is shorter than path B. You can calculate the path difference using simple mathematics, and that should be equal to 2d sine theta. If we want path A and path B to be in phase to have constructive interference, then the path difference should be equal to n lambda, where lambda is the wavelength of the wave. Now, this is what we call Brag's law. This is condition for constructive interference. When n is an integer, then the reflected waves are in phase, and this produces a bright spot on the diffraction pattern. So how do we determine the molecular structure? We need to measure the diffraction pattern for the different orientation of the crystal, And then in the simplest case, we put all the diffraction patterns together, and we apply a mathematical operation called Fourier transform to transform it into the three-dimensional space. However, this is the simplified version, and in practice, it's more difficult. Okay, now I want to do a quick comparison between X-ray diffraction, electron diffraction, and neutron diffraction. In X-ray diffraction, the X-ray interacts with the electron cloud of the sample. That means this technique works best if we have lots of heavy atoms in our sample. Since hydrogen has only got one electron, that means hydrogen is almost invisible in the X-ray diffraction pattern. The advantage of X-ray diffraction pattern is that it's cheap, and we only require a small amount to sample. In electron diffraction, electron interacts with both the electron cloud and also the protons of the sample. There is a possibility that the electron interacts with more than one atom. This makes the interpretation of the diffraction pattern more difficult. In neutron diffraction, neutron interacts with both heavy and light elements, and also neutron interacts differently with different isotopes, so this is a good thing. However, the neutron sources are very expensive, and we need either a nuclear reactor or a particle accelerator to produce neutrons. Another thing is neutron does not carry any charges, so that means the interaction of neutron with matter is not as strong as X-ray does with matter, and the consequence is we need a larger amount to sample. So you can see these three techniques are complementary to each other. If you want to get something, if it doesn't work on a particular technique, you can try to switch to another one and see whether you can find it out. Okay, let's summarize what we have seen so far. We try to see different matter on different length scale, and a diameter of human hair is in the millimeter range. Red blood cell is in the micrometer range. We can use optical microscopes to see these two objects. However, due to the resolution limit of optical microscope, we cannot see viruses, but we can improve the resolution by using particle waves, and we can see virus and atoms by electron microscopes. If you want to determine the structure of DNA or protein molecules, then we can use crystallography. We can also use particle waves such as neutron waves or electron waves to obtain the diffraction pattern. And particle waves are very powerful in allowing us to see matter at atomic resolution. And now this is the end of my part, and I would like to hand over to Professor Chu to talk about the LHC. Thank you very much.
Okay, so for the last 15 minutes or so, let me briefly introduce a huge experiment at so-called LHC, Large Hadron Collider. How this experiment enables us to understand what's inside a proton. So the LHC is the most powerful particle accelerator in the world. It's located in Geneva, near the border between Switzerland and France. It's about 26 kilometers in perimeter. So in the LHC, protons are accelerated to energy of 6.5 TeV. Okay? T here means 10 to the 12. So this is really high energy. If you think of it in terms of speed, then these protons are very, very close to the speed of light. Two beams of such protons would then be circulated around this accelerator, and then these protons will be collided in several places along the ring. In these particular places where they collide, we put detectors around the collision point so that we can record what happened during a proton-proton collision. So why do we do such experiments? Why do we spend so much money to build these particle accelerators? Why high-energy collisions? I give you three answers here. Right? First one, think of such a high-energy particle collision as a way to recreate the conditions at the Big Bang. Okay? You all know since kindergarten that the universe evolved over the last 13.7 or 13.8 billion years from a hot, dense state to the cold state we see today. Okay? So our universe began as a big, hot but small, hot and dense small fireball. We want to recreate that fireball in our lab by doing high-energy particle experiment, collision. Okay? So that's the first answer. We want to study how high-temperature physics evolved to low temperature, high-energy physics evolving to low energy. Secondly, Alvin just described to you how high energy or high momentum means shorter wavelength. So these high energy protons have very tiny wavelength, which means they allow us to see really tiny space-time length scale. So this allows us to probe very deep into the structure of matter, way deep inside any particles like protons or neutrons. So we want to look for fundamental constituents of matter. Third answer, after this collision, the fiber contains a lot of energy. So we hope to provide enough energy to create some massive but usually hidden particles. A side remark here is that today, from many different astronomical observations, we know that our universe is made up mostly of dark matter and not ordinary matters that we know of. The protons and neutrons, electrons, and so on, they are the absolute minority of the universe. We are quite sure that there are lots of other so-called dark matter out there. We don't know what they are. But we believe that they're massive particles. Maybe we don't see them around us because we don't have enough energy to create them. But this particle collision then provides a way to maybe to create these particles in the lab. So you can think of the high energy collision as a time machine, because it allows us to recreate the conditions in the early universe. So this allows us to look further back in time. You can also think of the LHC as a very powerful microscope. It allows us to probe very, very deep in space to the most fundamental constituents of matter. So this is LHC. You see these small circles. These are where the detectors are. And the experiment we joined is called the ATLAS experiment. It's here. It's about 100 meters underground. The detector itself is huge, 44 meters by 25 meters. So this is the size of a human being in comparison. Such a huge detector takes a lot of money and takes a lot of manpower to build it and then to operate it and to analyze the data. Give you some feeling of the size of the detector. Okay? So if you come to Chinese University of Hong Kong, this is a landmark. This is a water tower in the New Asia College. It's only 37 meters high, right? So if I stack the ATLAS detector right next to it, it's like this. So it's taller by about 1/3. Okay? I always like to imagine that we put this detector on campus. It would be quite a scene. So the people involved, there are about 3,000 scientists from all over the world, 38 countries or regions, 174 institutions. These numbers were changed about a year and a half ago. 2014 June, we add 3 to the number of institutions. You add the 3 institutions from Hong Kong. So Chinese University, HKU, and HKUST. Okay? We add 1 here because now Hong Kong is a member of ATLAS collaboration. In 2012, ATLAS, together with CMS, discovered the Higgs particle, the so-called God particle. And then the LHC was shut down for maintenance and for upgrade. In 2015, June, so about half a year before now, the machine was restarted. Now we're running the experiments at higher energy collisions, okay? 13 TeV, 6.5 on 6.5. The 2 beams of protons. This is one of the first events we saw in June last year. Okay? So we're very happy that it's now running and producing new data at high energy, high intensity, and many physicists are very hopeful that we'll discover new physics there. So this is a typical event. So the beam, you can think of it as going directly into the screen. Another beam comes out. They collide at this point, right at the center of the circles. These circles represent the different layers of detectors around the collision point. And they allow us to reconstruct all the particles that come out of this mini fireball, mini Big Bang. Okay? Right, now let me explain a little bit of physics here. Okay? So 2012, I explained that we discovered the Higgs particle. Let me tell you what it is about. Okay? There have been a series of questions about these fundamental particles, which I told you about in the beginning. Okay? So we believe that everything is made of the quarks, leptons, electrons, and neutrinos. Okay? But we also know the masses of most of these particles. So for example, U quark, the mass is 2.4 MeV. The top quark is 171 GeV, giga-electron volt. Electron mass is 0.5 MeV. We even know the masses of these gauge bosons. So photons, 0 mass. Gluons, 0 mass. But the Z and W, which are the force carriers of the weak interactions, are very massive. 91 giga-electron volt, 80 giga-electron volt. So if you just look at this picture, this standard model of elementary particles, naturally you should ask, why are these masses so different? If they're all elementary, how come some have 0 mass, some have large masses? What's the origin of these masses? Okay? What gives these particles their masses? That's the fundamental question we like to answer. Okay? Now let me explain 3 ways why this question has some significance even to you. Okay? I don't know whether you ever wonder what determines the sizes of atoms. Okay? Which, of course, determine the sizes of everything. Right? The answer is actually the mass of electron. Okay? So take an atom, Alvin told you the size of an atom, typical atom, right? It turns out that the radius of an atom is inversely proportional to the mass of electron. It's determined by the electrons, not the nucleus, okay? So that means if you change the electron mass, you change the size of atoms. For example, if you go to another universe, imagine there's a universe, the electron mass is only half of what we have. Then all the atoms in that universe would be double in size compared to ours. Okay? And then everything there. So that's one reason why we like to understand the electron mass. It's fundamentally important. Right? Second reason, in an atom, the electrons are bound to the nucleus because they have opposite electrical charges. So there's a binding energy. Okay? So it takes some energy to take away the electrons from the atoms. What determines that binding energy? Turns out, again, it's the electron mass. It's proportional to the electron mass. So again, now if you go to another universe where the electron mass is much smaller than our universe, then atoms in that universe can be ionized much easier, which means that matter in that universe would not be stable. Okay? There would probably not be any living objects in that universe. Third reason. I told you about the different fundamental interactions among the elementary particles, right? The electromagnetic interactions, weak interactions, and so on. It turns out that the ranges of these fundamental forces, again, will be determined by the mass of the force carrier particles. So for example, electromagnetic interaction is carried by photons, which has zero mass, so such an interaction would have infinite range. Same for gravity. But weak force being mediated by W and Z, and they are very massive, the range becomes much smaller, in fact, smaller than the size of a nucleus, and that's why you don't feel it in daily life. Okay? If you go to another universe, if the W and Z in that universe has a very small mass, then the weak interaction there would have long range, and you feel it on a day-to-day basis. A very different universe than ours. Okay, now, the next two slides, I'd like to explain the so-called Higgs mechanism, which gives rise to the masses of the elementary particles. But before I get there, let me explain the concept of mass. This is a famous equation which you learn in kindergarten. Okay? E equals mc squared. Right? What does it mean? It tells us that mass and energy are equivalent. Just that people before Einstein did not realize it. They use different units, and that's why we need the c squared there. They're actually the same thing. That's what Einstein realized. All right, now if you accept that, then the mass of any object must include not just the rest mass of its components, but also all kinds of energies within that system, including the kinetic energy, interaction energy, right? So let me illustrate that by several examples. Simplest example, imagine a box with two particles. Each one has a rest mass small m. Okay? They don't move, so they don't have kinetic energy. They do not interact, so they do not have interaction energy. The total mass of this box is simply 2 times small m. That's simple. But imagine another box with the same particles, but now the particles are moving around with some speed. Okay? So the mass of this system is no longer just 2m. But now you have to add the kinetic energies of these two particles. They are a part of the total mass of this system. Okay? Third example, imagine that now these two particles don't move around, no kinetic energy, but they interact. Okay? So one positive charge, one negative charge, so that they have a negative interaction energy. They attract each other. Okay? In this case, this interaction energy would reduce the total mass of the system. So it's no longer 2m, but slightly less than 2m because of this interaction energy. Similarly, if they have a repulsive interaction and there's a positive interaction energy, then the total mass could even be larger than 2m. Okay? Could be smaller, could be larger. Could be larger because of kinetic energy, or it could be because of interaction energy. Okay? So even if these particles individually have zero rest mass, I could still make up a composite system with a finite mass, which is the case for M2 and M4. So in M2, even if the small m is 0, the kinetic energy alone would give rise to a finite total mass of the system. Similarly for M4. And in fact, I don't know whether anyone has ever wondered where your mass comes from. Right? Your mass are, of course, the masses of the atoms, right? Many atoms. But where's the mass of the atom? Mass of the atom comes from the electron outside, but that's a tiny fraction, so forget about that. So mostly the mass of an atom comes from the mass of the nucleus. The mass of the nucleus, of course, comes from the mass of the protons and neutrons, right? One proton has a mass of about 1 gigaelectron volts over c squared. It's very similar for a neutron. But where does this mass come from? I told you that a proton has many quarks and gluons inside, okay? But what about the masses of the quarks and gluons? Well, gluons are massless. The quarks have some mass, but very small, only a few mega electron volts, so 1,000 times less than the total mass of the system. Okay? So now you think back at this example, with zero rest mass, then the mass comes mostly from the kinetic energy or the interaction energy. That is indeed the case with a proton. Okay? The quarks and gluons are more or less massless, but they move around speed of light, a lot of kinetic energy, and they interact strongly. The strong interaction energy contributes to the mass of the proton. So your energy comes from kinetic energy and strong interaction energy. Okay? Your mass. All right, if you accept that, let me explain the Higgs mechanism. So basically, the entire idea is to say that the masses of elementary particles comes from the interaction energy between them and a medium which we hypothesize to be hidden inside vacuum. So we imagine that the so-called vacuum is actually filled with something we call a Higgs field. Okay? So that acts like a medium which interact with the fundamental particles like an electron to give it its mass. Let me explain this with an analogy. Okay? So electrons propagating inside a crystal will feel some interaction from the ions inside the crystal. So they being of opposite charges, the ions would drag on the electrons. Okay? So this would then produce the so-called effective mass of the electrons in the crystal. This is well known and can be measured very well. Similarly, the Higgs field hidden inside a vacuum is like the crystal here, interact with the elementary particles like electrons, like quarks, and the interaction energy gives the masses to these elementary particles. So in this theory, all the elementary particles in a true vacuum would all be massless. But because our vacuum is actually filled with this Higgs field, and that's why they acquire the masses. Well, that might be a beautiful theory. It depends on the matter of taste. How to prove it? Okay? One possibility is that if the vacuum is truly filled with this Higgs field, then you should be able to excite this Higgs field by, for example, doing a high-energy particle collision. That's mini fireball would provide enough energy to excite the Higgs field so that you have excitations, and these we call Higgs particles. So you can produce a heavy, very massive, excited state of the Higgs field, and they're called Higgs particles, right? Let me explain that with an animation. So according to this Higgs theory, elementary particles should all be massless. They all travel speed of light. But our vacuum is actually full of this Higgs field, and the Higgs field interact with the elementary particles. And the interaction energy then is the mass of the elementary particle. So the way to probe it is to do proton-proton collision at high energy. Maybe you get enough energy to produce a Higgs particle, and it decays very quickly to other particles. If we discover this Higgs particle, then that would be a strong evidence of this picture of how elementary particles acquire the masses. In 2012, indeed, the Higgs particle was discovered with a mass of about 125 gigaelectron volts over c². This has opened up a new window to study physics because the Higgs field is now the fifth force. Okay? It's different from the electromagnetic force, strong force, and weak force. We have a completely new fundamental force. We don't know much about it yet. We don't know much about the properties of this Higgs boson yet. So this opened up a completely new window to look at new physics. Precision measurement of this Higgs particle of all its properties would then constrain our standard model and lead to perhaps new physics beyond this standard model that we were stuck with for many years already. I'm happy to say that the Hong Kong team I told you about, even though we're very young, we have already made some significant contributions to studying this Higgs particle. So we measure how this particle coupled to various other particles. So these are called Higgs couplings. We measure its mass. We have to measure its mass. We have to measure the spin of this particle as well as parity of this particle. Because of time, let me skip what other searches we're doing in the LHC. And so I skipped 3 slides, but show you some photos of our team members. So these are our students, mostly. These are undergraduate students, and then there are a couple graduate PhD students, postdoc, and there's an old man here. So every summer now, if you go there, in the summer, you'll see many students from the 3 universities in Hong Kong. They're working closely with experts from all over the world to study all sorts of things, including the Higgs properties and so on. So 2015, I think January, I brought 2 representatives from Science Museum and show them the ATLAS detector underground and so on. So I really hope that some of you will be there this July and meet our team members, discuss physics with them, and just see around and see how this operation is working. Okay, let me come to the end. Just to remind you that we have covered many, many topics now, right? So we have come down from very macroscopic systems, stars, how a star blow up, orbiting, merging black holes, merging neutron stars, how we study them, right? So we make use of neutrinos and gravitational waves, maybe, right? So these are the future observatories, and we're hoping that they will tell us a lot more that we haven't known by using optical, usual visible lights. Dr. Leung told you about using particle as waves to do microscopy. And that's how we know a lot of things, including even the structure of DNA and so on. And then the last part, I told you about the last paradigm, which is to break things apart by doing particle collision experiments. Breaking these particles then tell us a lot of new things, including even these hidden particles called Higgs particle, which we believe to be an excitation of the Higgs field, which gives rise to the masses of elementary particles. So I'll stop here. Thank you.
Thank you, Professor Ji and Dr. Lan. Now it would be the question and answer sections, please. Any questions? You can just raise up your hand. Yeah. 前面紫色衫係。
我用廣東話啦。我想請問點解美國佬嗰個費米實驗室會執咗笠嘅？有冇啲咩？
再講多次，聽唔到。
點解美國佬嗰個費米實驗室會執咗笠嘅？
哦。Okay, let me repeat the question in English first. Okay, the question is how come Fermi Lab, which is also a particle accelerator in the United States, how come it closed down? Right? Money, it's always money, all right? It's quite expensive to maintain an accelerator, and it doesn't get as high in the particle energy as LHC. So then it becomes sort of not so meaningful to maintain its operation. It actually tried very hard, and it's probably on almost at the edge of discovering the Higgs, but it didn't quite make it because it didn't have enough energy and intensity. Yeah, so too bad. Money is always money.
Any more? Yes.
Hi, Professor G. So I would just like to clarify. So you mentioned the mass of proton is coming from the kinetic energy of the quarks
and gluons.
And also the strong interaction and also the Higgs interaction.
Yeah.
Okay. So, but what about the gravitation? Where is it? I mean.
Oh. So let me clarify again. Take the proton mass, 1 GeV. About half of it comes from the kinetic energies of the quarks and gluons inside it. The other half, roughly, comes from the interaction energy, the strong interaction energy. The rest masses of the quarks and gluons, which comes from the Higgs, is actually a tiny fraction of the total mass, maybe a few percent. Right? What about other interactions? Now, the quarks also have electrical charges, so there are also electromagnetic interaction. That's even smaller because it's weaker than the strong force. So maybe 1%. Right? Small, very small fraction. You go down the list. Weak interaction. Yes, there are some weak interactions among the quarks. That's even a smaller fraction of the total energy. Okay? Gravitational interaction. Yes, in principle, there's a tiny, tiny contribution, but it's totally negligible.
Any other questions? Yes, here.
Dr. Chu, I want to ask a question because you have just mentioned about the Higgs theory. It seems that, according to the Higgs theory, it seems that all the particles have low rest mass, but all the rest mass come from the Higgs interactions. But according to the relativities, all the particles with low rest mass should move in the speed of light. But I just have a feeling that the Higgs theory is not quite consistent with the relativity. This is my knowledge not good enough so that I have this feeling on why is that?
Well, let me clarify one thing first, right? It's not true that all the elementary particles acquire their masses through the Higgs field. Very likely, the neutrinos are different. Very likely. Okay? Neutrino has some tiny rest mass, but probably through another mechanism, so-called seesaw mechanism. So maybe the neutrino mass has nothing to do with Higgs field. Okay? But forget about neutrinos for now. Okay? Back to your question. So if Higgs is correct, if the Higgs theory is correct, that means the elementary particles should all be traveling at the speed of light. Obviously, we don't see them. We don't see all the electrons traveling at the speed of light, right? So is there a contradiction? That's the question, right? No contradiction, because all these particles have some effective mass, which means that they slow down from speed of light to much slower speed. And that's why you don't see them as traveling at the speed of light. Okay? Now, it's not that abstract, in fact. Even light can be slowed down in some medium. We know that. You can measure that. Okay? There are even special media that you can even almost stop light. So you can think of it as even light can acquire some effective mass inside a medium. So the Higgs field is the medium. If it's there, then naturally the elementary particles all move slower than the speed of light, or they acquire some effective masses. 如果怕醜就用廣東話問喎，我唔怕醜喎。
有冇其他嘅問題想問 ？OK， 後邊。
我用中文問啊，唔好意思你頭先講過咧，佢嗰個叫做中微子咧，喺嗰個太陽嗰度即係製造出嚟啦。咁佢不斷咁製造，咁跟住其實佢嘅終極係會去到邊啲地方咧？或者永遠係存在？如果係永遠存在嘅，咁佢既然係一個製造，咁佢咪越嚟越多、越嚟越多、越嚟越多咯？我就係想清楚呢一樣嘢。
Yeah, very good. Let me translate the question first. I like this question so much, I'll answer it both in English and Cantonese. Okay? So the question is, I mentioned that all the stars, including our sun, produce a lot of neutrinos every second. Okay? So my way of characterizing stars are objects that turn ordinary matter into neutrinos and light. Okay? So the question is, what happened to these neutrinos? Do they exist forever? Where do they go? Okay? If they don't die, does it mean that our universe will have more and more neutrinos? Okay? The answer is yes, indeed. Our universe on the whole, because there are so many stars around, keep on producing neutrinos. There will be more and more neutrinos. Every second, there are many more neutrinos. There are less other particles. Okay? So the evolution of the universe is conversion of some of the ordinary matter into neutrinos, and the neutrinos don't die as far as we know. They just spread out, and they will eventually spread out uniformly in the universe. So this seems to be the fate of the universe. We'll be full of these ghost particles. Let me answer once more in Cantonese. 你講嘅完全啱㗎。啲星不斷製造中微子，中微子完全冇阻擋，一路向四方八面散出去。我哋到今日所知，佢哋永遠唔死嘅。其他粒子嘅數目會越嚟越少，中微子嘅數目會越嚟越多。咁宇宙一路演化落去咧，就會係充滿越嚟越多呢啲咁樣嘅幽靈粒子㗎。所以我好中意研究幽靈粒子㗎。
Yeah, thanks for the question. 問到一條問題。你話我成日即係我頭先一路咁聽咧，就你好似話嗰個叫做我叫做重力啊。咁你話就嚟可以揾到咁樣，即係我聽你咁樣講，但係至到而家即係我咁講其實係有你係咪有即係意味住嚟緊嘅技術就嚟可以揾到呢個重力咧
？Okay, again, that's a very good question. So the question is about the gravitational waves, 重力波，係咪？ I mentioned, I explained what they are. Gravitational waves are waves in space and time. Okay? Was predicted by Einstein 100 years ago. I mentioned that I believe they will be seen very soon. Okay? It's only my guess. Why did I say that? Let me just tell you a little bit of my own personal story, all right? I went to the States for my college. So I went to Caltech in 1980 as an undergraduate student. At that time, they built a prototype 4 meter by 4 meter gravitational wave detector. And I went to visit that prototype. I thought, oh, that's cool. We can see whether Einstein is correct or not. I actually thought seriously about joining that experiment. That was 1980, 35 years ago. Most of you were not even there, right? We did not even exist at that time, right? After 35 years, now they have so-called advanced LIGO, which just got turned on a few months ago. Okay? The advanced LIGO, there are two detectors. One in the northeastern part of the United States, one in the northwestern part, and then the other one in the southeastern part. Okay? They're identical, 4 kilometers by 4 kilometers. The sensitivity they reached is already, if I'm correct, I'm not absolutely sure, but I believe that they have already demonstrated that they reach a sensitivity of about 10 to the minus 22. What do I mean by that number? That number means they can measure the difference in length, 10 to the minus 22 parts out of this 4 kilometer arms. If you calculate it, this is absolutely amazing. They can detect 1,000th of the length of a proton out of a 4 kilometers arm. According to most astrophysical estimates, this sensitivity, they should be able to detect merging black holes and so on. If they still don't see it, there are 2 possibilities. One is that Einstein is wrong. Nobody likes it. Well, maybe everybody likes it. Okay? But that would be very exciting, right? I would say that's unlikely. Second possibility, the astrophysical estimations are wrong. So what we know about black holes, neutron stars, maybe those are wrong. Right? I would say it's possible, but I also think it's unlikely. So I would bet my money on discovery of gravitational wave soon.
Okay, thank you, Dr. Ji and Professor Ji and Dr. Leung. Thank you for joining this lecture. The PowerPoints and the videos of this lecture will be uploaded to our museum's website next week. Thank you, everyone. Thank you.
Thank you.